Hello friends, today's question. In the circuit, L is 1 microhenry, capacitance is 1 microfarad and resistor is 1 kilo ohm. They are connected in series with an AC source V is equal to V0 sin omega t as shown in figure. Which of the following options is or are correct? And this question came in the 2017 advanced question, and we are going to solve. I think there are 3 questions from 2017 advanced. In the first one, so we have to find out which of the following is correct options. There are total 4 options. First of all, we are going to find out the resonant frequency, and because it says that the current will be in phase with the voltage if omega is equal to 10 raised to power 4 radian per second. So which basically means that the current in the series LCR circuit, the current will be in phase with the voltage when the inductive reactance and capacitive reactance, that is at resonant frequency. Okay. So we start from here only, that in series LCR circuit, the current is in phase with the voltage at resonant frequency. At resonant frequency, or we can also say our XL is equal to XC, and based on this relationship XL equal to XC, we can find out our resonant frequency, that is omega naught, will be equal to 1 upon square root of LC, and value of L and C are given to us, so we substitute them. It comes as 10 raised to the power minus 6 multiplied by 10 raised to the power minus 6 and its square root. So this comes as 1 upon 10 raised to the power minus 6 and is equal to 10 raised to the power 6 radian per second. So therefore, and in the question it is not written as omega naught, but it is written as omega. Therefore, we can say that our omega naught as per question is equal to omega, and that comes as equal to 10 to the power 6. Whereas in the question itself, it is given that for option C, that omega should be equal to 10 raised to the power minus 10 raised to the power 4 radian per second. Therefore, we can say that our option C is incorrect. Okay, so this option is C option is incorrect. And next, we are going to find out that the frequency at which the current is in phase with the voltage is independent of R. Okay, option number B, it says that the frequency at which the current will be in phase with the voltage is independent of R. So obviously, this particular frequency is, like I said, is called as a resonant frequency. Okay. So let me write it here. You can say the current is in phase with voltage, that is at resonant frequency, and which we call as omega naught. Our question is equal to omega, and we can also write it as f naught, and that will be equal to over f. So any of these two will be same. And the option number B, it said the frequency at which the current will be in phase with the voltage is independent of R, and the resonant frequency is our omega naught. So our omega naught is only dependent upon inductor and capacitor, that is L and C. So this is independent of, you can say, our R, or here we can also write that F naught is equal to 2 pi upon LC. So from here we can say that the resonant frequency depends only on L and C, that is independent of R. So this option number B is correct option. So you can say option B is correct. Now let us discuss the behavior of the circuit, that is option number A, when omega is approximately equal to 0 or tends to equal to 0. So here it says the current flowing through the circuit nearly equal to 0. Let us test this option number A. So we say behavior at omega tends to 0. So which means omega is approximately equal to 0. And our inductive reactance, the formula inductive reactance, that is XL, is equal to omega L, and our capacitive reactance that our XC is equal to 1 upon omega C. Therefore, under the condition that when omega tends to 0, we can write that as omega tends to 0, our XL tends to 0. So therefore we can say it inductor behaves like a short circuit. Inductor behaves like a short circuit, and under the same condition our XC tends to infinity. Therefore capacitor behaves like a open circuit. Capacitor behaves like a open circuit. So obviously, as it is a series LCR circuit, the capacitor is going to act as open circuit. Therefore the current in the circuit will be nearly equal to 0. So we can say that thus for series LCR circuit, the current in the circuit if current in the circuit becomes nearly equal to 0. Nearly 0. So this option number A is our correct option. You can say option A is correct. And the last, we are going to find out when the omega is very much larger than 10 to the power 6 radian per second. The last, we see that omega is very much greater than 10 to the power 6 radian per second. So in this case also, we can write that our inductive reactance, that is XL, which is omega L, it increases significantly because there is a direct relationship between omega and inductive reactance. So XL increases significantly. And our XC, which is 1 upon omega C, under this condition decreases significantly. So it increases significantly, so we can assume that it becomes approximately equal to as open circuit, and XC decreases significantly. Or we can say that it approximately be equal to short circuit. So under this condition, XL will be very much larger than XC. XL is very much larger than XC, or from here we can draw a conclusion that inductor acts as a dominant impedance. Inductor acts as a dominant impedance. Thus, in the option, it is mentioned that the circuit behaves like a capacitor, which is not true, because the frequency which is larger, the circuit behaves as a inductor. So this option is also incorrect. So inductor acts as a dominant impedance, therefore option D is incorrect. So this completes the first question. Now we come to the next, which was also asked in 2017 advance, and in this case it was given that we have the instantaneous voltages at the three terminals marked X, Y, Z are given by Vx, Vy and Vz, and it is governed by the equation that Vx is equal to V0 sine omega t, Vy is equal to V0 sine omega t plus 2 pi by 3, and Vz is equal to V0 omega t plus 4 pi by 3. An ideal voltmeter is configured to read RMS value of the potential difference between its terminal. It is connected between points X and Y and then between Y and Z. The readings of the voltmeter will be. So this is also a multi-correct, you can say, question, and it is given to us that the voltmeter is initially connected between points X and Y, and then it is connected between Y and Z. So we have to find out basically what will be the reading between points VYZ and points VXY. based on this, all the options can be mostly verified. We can see which is, for the solution of which we require some other things. So we are given that instantaneous voltage at 3 terminals. So let us first of all write those. We are given that Vx is equal to V0 sin omega t. We have our Vy, which is equal to V0 sin omega t plus 2 pi by 3. And finally, we have our Vz, which is equal to V0 sine of omega t plus 4 pi by 3. And it is said that the RMS voltage is being measured, and the points with which it is being measured, first of all, is between x and y, and next is between y and z. So between x and y, let us call them as vxy, and between y and z, let us call that as vyz. So first we are going to calculate our vxy. So vxy is equal to voltage at x minus voltage at y, and we simply substitute the value of Vx and Vy, which is given to us. V0 sin omega t minus V0 sine of omega t plus 2 pi by 3. And V0 will be our common, and then we can use the trigonometry identity to solve it. So this will be equal to our V0, and this comes as 2, so we can write 2 V0 and cos of 2 omega t plus 2 pi by 3 divided by 2 multiply by sine of minus a minus b, that is 2 pi by 3, and divided by 2. And we know that sine of minus x is nothing but minus sine x. So we can just write it that our Vx y will be equal to minus 2 V0, and this we can solve at cos of, this comes as omega t plus pi by 3, and this also comes as sine of pi by 3. Because 2 and 2 cancels, and here also this goes throughout 2, and this also gets 2, and we know that our sine of pi by 3 is square root of 3 divided by 2. So we substitute the value, we get Vxy is equal to minus 2 V0 cos of omega t plus pi by 3 and multiply by square root of 3 divided by 2. This 2 goes with 2, and we are left with Vxy is equal to minus square root 3, and we have V0 cos of omega t plus pi by 3. And it is reading as RMS value. So these are the peak value. So we need to associate the RMS value. So this is our basically nothing but a peak value. And from here we can find out our RMS value. We can say Vrms is equal to peak value divided by square root of 2. This comes as V0 square root of 3 divided by square root of 2, and this comes as V0 square root of 3 divided by 2. Similarly, okay, let me check. Yeah, so B part is correct one. So from here we can say part option B is correct. Is correct. Similarly, we can find out our first part, A part, that is 𝑽x. Once again, same method, 𝑽z is equal to 𝑽y minus 𝑽z. We substitute the value. This is our V0 sine of omega t plus 2 pi by 3 minus V0 sine of omega t plus 4 pi by 3. And we can just shortcut it now, and we are going to get this as 𝑽z is equal to, this will be equal to our V0 will be common, so this comes as 2 V0, and here we have a cos of omega t plus pi, and we are left with sine of pi by 3, and cos omega t plus pi is nothing but minus cos omega t. Okay. So we can solve this part, and from here we get our 𝑽z will be equal to minus of 2 V0 cos of omega t and sine of pi by 3. We still, sine of pi by 3 is root 3 by 2. So we substitute here, we get root 3 divided by 2 and 2 cancels out. So from here we get this as minus square root of 3 V0 cos of omega t. And once again we are interested in RMS, so we can find out, okay, let me, here I have to make a slight correction. This is our 𝑽x 𝑽 RMS. Similarly, here we can write our 𝑽z RMS is equal to, and this comes our, it will be same, that it will be equal to our V0 square root of 3 divided by 2. Okay. So from here we can at least say that both 𝑽x 𝑦 is equal to 𝑽z. So option number A is incorrect. Option A is incorrect. And next, it is said that independent of choice of two terminals. So basically it means that, like in one of the options, or we can say one of the solution, we found out our 𝑽x, this one. So here we calculated 𝑽x as 𝑽x minus 𝑽y. Okay. Similarly, we calculated 𝑽z and as 𝑽yz as 𝑽y minus 𝑽z. So let me write it here, that we found out 𝑽x is equal to V0 square root of 3 and cos of omega t plus pi by 3. And similarly, we found out that our 𝑽z is equal to V0 square root of 3, and we got this as cos of omega t. Okay, we are not interested in negative sign, doesn't matter. And we can also calculate that our 𝑽zx, which will be equal to Vz minus Vx, and that will be equal to our V0 square root of 3, and this comes as cos of omega t minus pi by 3. And for this also the RMS value, that our Vzx RMS will be equal to V0 square root of 3 divided by 2. So in all the three cases we found out that Vxy RMS is equal to Vyz RMS, and this is equal to Vzx RMS. So it means the voltmeter reading is independent of which terminal we choose. You can say voltmeter reading, because it is measuring RMS voltage, we can say voltmeter reading is independent of which two terminals we choose. So the option number C, sorry, not C, I think this is, yeah, C is also correct. Option C is correct. And finally, we are left with only one option, that Vxy RMS is equal to V0. Okay, so which is also incorrect, because we just found out that option number B is correct. Okay, so option number D is automatically incorrect. So let me put it here where we found out this as, yeah, here. So from here we can say that option D is incorrect. Option D is incorrect. So this completes this particular question, and we come to our final question, which were also asked in a 2017 advance. And here it was given that a circular insulated copper wire loop is twisted to form a two loops area A and 2A as shown in figure. At the point of crossing, the wires remains electrically insulated from each other. The entire loop lies in the plane of the paper. A uniform magnetic field B points into the plane of paper. At t is equal to 0, the loop starts rotating about the common diameter as its axis with a constant angular velocity omega in the magnetic field. Which of the following options is or are correct? So this is also multi-correct option. So this is a given figure. So we have a loop which resembles like 8, only that the point of crossing, they are not touching each other. Lower one is given as 2A, upper one area is given as A, and it is rotating along the diameter, common diameter, in the magnetic field which is into the paper. So let us start, because more or less it is here it is every option more or less is related with EMF or rate of change of flux. So they are interconnected with each other. So let us start with our flux introduced flux through each loop. So you can say magnetic flux through each loop. Magnetic flux through each loop. And the general formula for magnetic flux, if you rotate any loop which is rotating in the magnetic field B, it is given as phi is equal to BA cos of omega t. And we can generalize this formula for smaller loop and a larger loop. So we can say for given two loops, smaller loop which is having area A, let us call that as phi 1 is equal to B A cos of omega t, and we have a larger loop whose area is given as 2A, let us call that as phi 2. So this becomes as 2BA cos of omega t. Now we find out the induced EMF. Induced EMF, the general formula is minus d phi by dt. Similarly, for two loops, first of all we write it for smaller one. Smaller loop, we get, let us call that E1 is equal to minus d of dt of phi 1, and we can write that our E1 is equal to minus d of dt BA cos of omega t, and this comes as our BA omega sine of omega t. And then for larger loop, E2 is equal to minus d phi 2 by dt, and this comes as 2 BA omega, and we have sine of omega t. And the net induced EMF, net induced EMF, and we can see from the figure that the smaller as well as larger loop, they are oriented oppositely, okay, because the figure 8 is formed. So orientation is different. So because of this, the EMFs will be subtractive in nature of area A and of area 2A. Sorry. Therefore, we can say that since two loops are oppositely oriented, due to figure 8, their EMF will subtract. Therefore, we can write that our net EMF will be equal to E2 minus E1. So this becomes 2 BA omega t sine of omega t minus BA omega sine of omega t, and we get our E net is equal to BA omega sine of omega t. I think one of the option was that it is given is proportional to the sum of areas of two loops, whereas it is we can say it is not proportional to the sum, but it is negative of the sum. So option number A is incorrect. And next, from here we can say option A is incorrect. Is option A is incorrect, and option B, it is given that amplitude is maximum. Let me 1 second. The rate of change of flux is maximum when the plane of loop is perpendicular to the plane of the paper. Okay. The rate of change of flux is maximum when it is the plane of paper. So we come to the option number B, and you can say from here that the amplitude of the maximum net EMF induced due to both the loops is equal to the amplitude of maximum EMF induced in the smaller loop. Induced in the smaller loop alone. And next is our that option number C is the net EMF induced is proportional to cos of omega t, whereas we found out the EMF induced in E1 and E2 is proportional to sine omega t. It is proportional to sine, not to cos. Therefore, option C is incorrect. And finally, we come to the option number D. The amplitude of the this is option D, so it is correct one. This discussion is option D. So this is also correct. And we come to option B actually now. And it is said that EMF E, which is our minus d phi by dt, and we know that our phi is equal to BA cos of omega t, and rate of change of flux, we can say our d phi by dt is equal to minus BA omega sine of omega t. And for flux, this rate of change, I think it was asked rate of change. Yeah, rate of change of flux. So we can say rate of change of flux, that is of d phi by dt, is maximum when our sine of omega t is equal to plus minus 1, and this happens when plane of the loop, or we can say loops because we are having two plane of loops, is perpendicular to the plane of the paper. Plane of paper. So option D is also correct. D is correct. So not option B is correct, C is incorrect, and D is also correct. I mixed them. So here the option B is correct. So these were the three questions that were asked in 2017 advanced paper, and this completes all the three questions. Thank you.